In this video, we're going to do something really nifty. We're going to project one vector onto another. So just to get started, let's draw some pictures. So we're sitting out here on the Cartesian plane. Say we have a couple of vectors. We'll call this one u and this one v. Finding the projection of u onto v is basically doing this. So you think about, like, you want to figure out how far you need to go along v so that if you make a left turn, a sharp left turn, you'll get to u, right? So this is this becomes a right triangle, and then we have this vector. This is the one we're after. So this is the projection of u on to v. And there's some really clunky notation for this. So people will sometimes write this vector as, it's the projection of u onto v is how you read that, but it's subscripted v. And then the argument kind of this function is u. All right, so how are we going to do this? How are we going to find this, this vector projection? We know that this projection of u onto v is a vector in the direction of v of length, well, I don't know what the length is. It's this length. If I know how long that side of that triangle is, then I can use that value to make a vector in the direction of v that has that magnitude. We'll start off by finding a unit vector in the direction of v, and we know how to do that, right? Because we did it a couple of videos back. So to get the unit vector in the direction of v, we just take that vector v and we multiply it by the scalar 1 over the length of v. And so I'm going to write this a little bit more compactly as the vector v divided by this scalar. So let's just make a note of this. Remember that this is a scalar. It just means it's a plain old number, and that means we're going to divide every value, every component of the vector v by the value of the magnitude of v. All right, so if we find this vector that's in this direction of v, then the vector that we're looking for is just going to be equal to that length, that unknown length as of yet, times this unit vector in the direction of v. So how are we going to find this length? So we can find this length by using that formula that we use to find the angle between two vectors, together with a little bit of trigonometry. So I'm going to just copy that right triangle that's suggested in that diagram. I'm going to copy that down and just make notes of what we know about this. So this is the length that we're after, right? That one leg of the triangle. There's an angle here that's situated at the origin, and then we know the length of the hypotenuse of this triangle, right? It's the length of that vector u. We don't know the length of the other leg of the triangle, but we do know trigonometry. We know that the cosine of the angle is equal to the magnitude of the adjacent side divided by the length of the hypotenuse. All right, so we can figure out what that unknown length is now just one step of algebra, right? So the length of u times the cosine of the angle between those two vectors. And if we do a little bit more, messing around with this, we can imagine using that dot product formula from last time, right? So from last time, we know that the cosine of theta is equal to the dot product u dot v over the magnitude of u times the magnitude of v. That was the formula that we used last time. So if I just substitute that in for the cosine of theta, then I can compute this question mark length without even having to worry about computing the angle. I can compute it just straight from the vector components themselves. So to summarize, if we want the projection of vector u in the direction of vector v, what we're going to use is this formula, right? So we're going to take the length of u times cosine theta, but cosine theta is actually this, and multiply that by this unit vector in the direction of v. Now we can do some combining and some canceling and stuff. Why don't we do that just quickly? So this u magnitude will cancel with that u magnitude. This is already a scalar, and this thing here is a vector. And we can put these together to make the length of v squared. So tidying up, we're going to end up with this. So we'll have u dot v divided by the length of v squared times that vector v. And again, just keeping track, this is a scalar. So this is the length we were after times the unit vector in the direction of v. Okay, so now let's try actually computing one of these things. Let's take a vector u, minus 1, 3, 2, and take the projection of that onto vector v, let's say 1, 1, 1. So we're going to find the projection of u onto v. And now that we already did all the reasoning and the work, we can basically just use this formula that we've got here. So there's a few things I need to compute. One is u times v, the dot product times. And we know how to do that, right? So this is just going to be minus 1 times 1 plus 3 times 1 plus 2 times 1. So that's 4. And then we also need, let's see, we need the length of v squared, right? So the length of v squared is, the length of v is going to be a square root, but then when we square it, that'll undo the square root, right? So this is just going to be 1 squared plus 1 squared plus 1 squared. So that's equal to 3. So now we can just use the formula and write down this vector projection. Right? We've figured out already u dot v is 4. And the length of v squared is 3. And then our vector v is just 1, 1, 1. So if I really want to write this out, we've got 4/3, 4/3, 4/3. All right, I don't think I'll try and draw a picture of this because it'll just end up being super messy. So here's a problem for you to try. Why don't you find this vector projection and draw a picture. All right, so pause the video and work it out. So this is the answer I got. When I computed it out, I get a vector with components negative 0.85 in the x direction and then 0.68 in the y direction. And if I plot that, it is a vector that's pointing backwards a little bit, right? So that's that orange vector right there. And what's happening is when we project u onto the direction of v, that orthogonal projection, that perpendicular projection, is actually ending up coming down behind where v is, but in that same direction. So this is how we find projections of a vector onto another vector.